Atoms are mostly empty space. At their exact center lies the nucleus, a structure roughly 100,000th the size of the atom itself. Because we cannot measure it through direct observation, we must determine its physical dimensions through mathematical derivation. A nucleus is built from tightly packed protons and neutrons, collectively called nucleons. The total count of these nucleons is the mass number, represented by the variable A. As more nucleons are added, the nucleus occupies more space. Because these nucleons pack together tightly and attract each other equally, the structure naturally settles into the most efficient three-dimensional shape, a perfect sphere. This packing model leads to a foundational rule. If every nucleon occupies a uniform amount of space, the total volume of the nucleus, V, is directly proportional to the mass number, A. This starting axiom is defined in the first line of the derivation notes. Volume is proportional to A. To calculate the volume of our spherical model, we use the standard geometric formula, 4/3 pi r cubed, where r is the radius. Substituting this formula for the volume variable yields a new relationship. 4/3 pi r cubed is proportional to A. The second line of the notes confirms this exact substitution. By linking the nucleon count to a geometric volume, we have the mathematical framework necessary to calculate the physical radius of any element's nucleus. Our next step is to isolate the radius variable r to see how the size of the nucleus scales as the mass number increases. In a proportionality, constants don't change the scaling relationship. We drop the 4/3 and pi, simplifying to r cubed is proportional to A. Taking the cube root of both sides leaves radius r proportional to a to the 1/3 power. The derivation notes track these algebraic steps, arriving at this specific scaling relationship. To convert this proportionality into a functional equation, we must introduce a proportionality constant. For the nuclear radius, we use the constant r0. This creates our final equation, r equals r0 times a to the power of 1/3. This boxed result serves as the formula for all subsequent nuclear size calculations. Experiments have measured the value of r0 as 1.2 times 10 to the negative 15 meters. Since 10 to the negative 15 meters is a standard scale in particle physics, we use the unit femtometers, making the constant exactly 1.2 femtometers. This formula allows us to compare two different nuclei. By taking the ratio of their radius equations, the r0 constants cancel, leaving a direct comparison based on their mass numbers. The final boxed equation in the notes defines this comparative ratio. We have successfully derived the mathematical relationship that dictates how the radius of a nucleus expands as mass is added. With the size of the nucleus defined, we can now investigate the density of the material within it. Density is defined as total mass divided by total volume. We start with the numerator. The variable lowercase m represents the average mass of a single nucleon. If m is the mass of one nucleon and a is the total number of nucleons, then the total mass of the entire nucleus is m times a. To find the nuclear density, ρ, we place the total mass in the numerator and the spherical volume formula in the denominator. We substitute the generic radius, r, with our derived scaling formula, r0 times a to the 1/3 power. Cubing the denominator makes r0 cubed and cancels the exponent on a, leaving a standard a. The notes showed this result, m times a divided by 4/3 pi r0 cubed times a. The mass number variable a appears in both the numerator and denominator. Being common to both, it cancels out entirely. The remaining equation consists only of constants, 3 times the nucleon mass, divided by 4 pi r0 cubed. The notes confirm that this final value is a constant. This cancellation proves nuclear density is independent of mass number. No matter how many nucleons are present, the internal density does not change. By inputting the known values for the mass of a nucleon and the radius constant, we can solve for this universal density. The calculation yields 2.29 times 10 to the 17th kilograms per cubic meter. This constant value shows that nuclear matter behaves like an incompressible substance, a material that maintains a fixed density regardless of the number of particles packed into it. Whether we look at carbon or uranium, the core density remains the same. We can apply this concept to resolve a common misconception in nuclear physics. Consider this problem. we have two nuclei with mass numbers in a ratio of 4:3. We need to determine the ratio of their densities based only on the fact that one is heavier than the other. The problem provides 4 possible mathematical ratios to choose from. Intuition might suggest that a nucleus with more mass would have a higher density, leading to a ratio like 4:3. However, our derivation proved that the mass number, A, cancels out of the density equation entirely. The density is not affected by how many nucleons are present. Since density is a constant for all nuclei, the first nucleus and the second nucleus must have mathematically identical densities. Because the densities are the same, the ratio between them is exactly 1:1. The notes confirm that the correct answer is option 3, a ratio of 1. While the periodic table is defined by a wide range of atomic masses, the internal density of every nucleus is a single, unchanging constant.